All right, today is Physics 1A, and we're going to be talking about pendulums. And I want to say something in general about periodic motion, okay? And that's to say that, in general, this chapter is on simple harmonic motion, or periodic motion is a better way of saying it, because simple harmonic motion refers specifically to a very special type of system. So, periodic motion, there's really two requirements for this. Okay. The first requirement is you need to have some type of equilibrium position. Okay. And then the second thing that you need, equilibrium position is a position where all the forces are balanced effectively. The second thing you need is what's called a restoring force. Okay? And the restoring force is just a force that drives the system back to equilibrium. It's a force that drives the system back to equilibrium. Let me just type that out. I don't want to write in this tiny little area here. Okay? It's a force that drives the system to the equilibrium position. So to give you an example of how that works, right? Like last time we were talking about a system where we had, a box that was attached to a spring, and we said suppose that the spring is stretched to some position, right? Like let's say the box is like right here, right? We said you've got a box, you've got a mass, you've got a spring constant. Those are the key things you need to know about it. And we said that the equilibrium position in the system is the position we call x equal to 0. It represents the place where the spring is unstretched, so that the net force acting on the object is 0. And then the restoring force in this case is a force that acts on the box backwards this way, F sub s. And we said, of course, that it's equal to negative k times x, where x is the distance right here that can be positive or negative, right? But that force is the restoring force, okay? And the x equal to 0 position is the equilibrium position, right? As long as you have these two things, you're going to have a system that's going to exhibit periodic motion. That means a system for which you can calculate the period of the motion, the frequency of the motion, as well as all kinds of other things, such as the position as a function of time, or with a pendulum, the angle as a function of time, etc. Okay, but any system that acts like this will automatically exhibit periodic motion, and periodic motion means that you can find a period to a motion. Okay. What are some examples of this? So, one example of this is the box on the spring, right? Let me tell you something that's not an example of this. Suppose I have a surface, like a table, right? And on this table, I place some type of long, tall cylinder, okay? So it could be just like a pipe or something like that, right? Whatever. We just put it end on end, right? We set it on its end here. Okay. Now, you could imagine, right, that this could be a type of equilibrium position. The box is balanced in the sense that the two forces acting on it cancel each other out, right? There's an upward normal force and there's a downward force of gravity, and it's balanced, right? And you could also imagine that if you were to push this box in this direction, this pipe in this direction here, that if it was tilted by just a little bit off to the right and you let go, that the object would basically wobble back and forth, and it might come back to this equilibrium position, right? But if you push it with too much force, then at some point the object is just going to fall over, right? And it will never return to this position again. So this is a type of what we would call unstable equilibrium, in the sense that it can be very, very easily disrupted, right? An unstable equilibrium. It would just fall over. It wouldn't exhibit periodic motion. If you push it hard enough, it's just literally going to fall over, right? So even though there's an equilibrium position, there is no restoring force. There's nothing to make it bounce back up to the equilibrium position. So we call that unstable equilibrium. So that's an example of something that's not going to exhibit periodic motion, even though it has an equilibrium position, mostly because it has no restoring force. Okay. An example of something that does fit these criteria, though, is what we call a pendulum. Pendulum is a very simple object. It's quite literally you have some type of a ceiling or something, or a fixed pivot point, and from this you hang a ball from a string. You've got some ball of mass m. You've got a string that has length l. Okay, and you can imagine that if you displace this in this direction here, where the ball now ends up at this location. Oops. Oh, my drivers are working again. How about that? I noticed that it seemed a little bit cleaner. So if you move it to this position here, where there's some angle theta that you make right here, right? Then I think you guys would agree that if you label the forces that act on the system, you're going to have some tension force acting like this, right? You're going to have a weight force that's acting, oops. A weight force that acts straight down, right? And then this weight is going to have a component that's going to tend to drive the force back this way, right? Sorry, drive the ball back in this direction. And then the ball would pass through equilibrium. This is the equilibrium position, right? It would pass through the equilibrium position, and then it would swing to the opposite side until it was, maybe somewhere over here at about the same angle, or probably a little bit smaller in real scenarios. And at that point, the force that's going to drive it back is going to drive it back this way, right? So this is your restoring force. And what is the restoring force? Well, I don't know how well I can draw it on here. I'm going to draw a better picture of this. The restoring force is whatever component of the weight kind of points along, like, tangent to the path, right? Okay, so we'll draw that in a bigger picture here, right? But this is an example of a system that's going to exhibit periodic motion because it combines an equilibrium position with a force, right, that always points back to that equilibrium position. So it's guaranteed to exhibit periodic motion. And all we need to do is to ask the question, what's the period of this motion? What's the period? And what is the angular frequency of this motion? Those are the two things we want to figure out. We would assume that they're going to depend on some things. What do you guys think they would depend on? T and omega, what are they going to depend on? Remember that in the system with the mass on the spring, this system, we found out that the angular frequency was a function only of k, the mass, and that's it, right? The amplitude did not feature into this, right? So these things will depend on length, definitely. That's one of them. What else would it depend on, or possibly depend on? What are the other features of the system that might be important? What about these two? Think it'll depend on gravity? Okay, like maybe a pendulum on Earth and a pendulum on the moon might be a little bit different. A pendulum on the Earth and a pendulum on Mars might be a little bit different, right? That's reasonable to think, right? If gravity's stronger, there's going to be a bigger force driving it to the middle. When you say distance, do you mean the distance that you displace it from equilibrium? Like the angle, maybe? Miguel? Okay, let's see if that's one of them, maybe. And then what else? What would be the only other thing that we really even have in the system? Other than, like, the tensile strength of the rope or something. But we're trying to find frequency, basically, Bia, so that's part of what we're looking for. What about the mass? Would the mass be part of it? So this is the question. Do you think, are all these, out of all of these, so you're saying maybe not mass. You're saying maybe not this one. Okay, let's see. Let's see which ones these actually depend on here. All right, let's draw a little more kind of like a picture that we can draw some, some things on. So say that's our ceiling, like black. And then from the ceiling, we're going to hang a ball. So we're going to hang a ball like right here. And let's make it about that long. Copy, paste. And we're going to have to displace it. So what we'll do is we'll put it right on off to the side. And then we'll tilt it a little bit. And bring it back together. There we go. It's the same length, so we can actually draw an arc through here of a circle. Maybe we just put it right on that location, just in case. Okay. God, that doesn't look like it's going to fit a circle in there, but whatever. And then we drop a ball. All right, here. Copy, paste that. Put it right there. Okay, so now we're going to say we have a chord with length L and a ball of mass m subject to a gravitational field that goes this way. And say mass here. And if we label the forces that act on the ball, the forces that we're going to get are like, I don't want to do any shape. There's going to be one force, let's use red for this, that's going to point red, shapes, arrow. And it doesn't really want me to do that, I don't think. Put it right there. And we'll stretch it like that. Okay, something like that. And then we'll shift it over a little bit. Like right there. Okay. So that's our tension force right there. The only other force acting on this object is going to be the weight. So we'll put the weight pointing down right here. And now what I want to do is I want to try to make it, I'll eyeball this a little bit. We're going to put this right here so I can actually make this the right length. I'm going to delete that arrow, it's just a guideline for me. Something like that. Delete this for now. That's going to be the weight of the object, mg, and then I'm going to define the angle here to be theta. Those are all of our forces that are acting on our system. Now the next thing I want to do is I'm going to basically look at the system and say that this tension force and this weight here, well, there's going to be some component of the weight that points in the kind of off in this direction here, what we call the radial direction. So what I'm going to do is I'm going to call this direction to be the radial direction. Positive radial direction is going to point that way. And then in the other direction, what I'm going to do is I'm going to say we're going to have two components for the weight. Those components are going to point both tangent to the circle. So one component's going to point like this. And the other component is going to point like this, at right angles to each other. Those are going to be the components of my weight force. And of course, we can copy paste this down to here to show that it's the right length, and it kind of isn't actually. We want to tilt it like that a little bit. Copy paste. Copy paste. There we go. So that's our two components, right? And then we can say, well, if this angle at the top right here is theta, then this angle is also going to be theta, which means that our components for our weight are going to be on this side, mg cos theta, and on this side over here, they're going to be mg times the sine of theta. And we're also going to say that yeah, so we take a mass, we displace it by some angle theta, and then we define the direction that's tangent to the path. This direction here is going to be the positive tangential direction. So we got radial and tangential directions, right? And what I'm going to say here is that we're going to use Newton's second law and state that if we sum up the forces acting in that tangent direction, that they should be equal to the mass of the object multiplied by its tangential acceleration. Now, there's only one force in the tangential direction, and it's this force right here, which is mg sine theta. So there's going to be an acceleration in that same direction. That's our a tan. Ooh, it looks kind of hard to read, isn't it? Sorry, A-T-A-N. And that's going to be something that's going to be part of our calculation here, right? So, how many forces do we have acting in the tangential direction? There's just this one here. So we say mg sine theta is going to be equal to the mass of the object times the tangential acceleration. But we know something about how the tangential acceleration is related to the angular acceleration. Imagine that this object is swinging back and forth and back and forth and back and forth and back and forth, right? That's what a pendulum does. Then you could define the rate at which the angle is changing, right? And what do we know about that? If I know something about an angle, and then I talk about the rate at which the angle is changing with respect to time, what does that give me if I take the rate of change of the angle with respect to time? angular velocity, right? We call that one omega. And then what if I take the derivative again? What if I take the second derivative of theta with respect to t? What does that one give me? That one's the alpha, right? The angular acceleration, right? So this gives me angular acceleration. But then what about a tan and alpha? How are those related to each other? How do I go from angular acceleration to the tangential acceleration? Multiply the length. That's exactly right. Okay, so what I'm going to do is I'm going to say, let's replace a tan in this equation over here with just L times alpha. Okay, and then acknowledge that we know this is true. So the angle that shows up on the left-hand side of this equation is actually related to that angle over there. But something else has to be put in here. Because if we think about what we've done, we just said outright that the force that's acting here is mg sine theta. But the thing is that the angle theta is defined like this, right? And I would say that this would be the positive theta direction. And that if we had an angle that went off to the other way, that's going to be the negative theta direction, okay? Think about this. This is like the clockwise direction. Sorry, counterclockwise, right? And when we define angles, counterclockwise is always positive, and clockwise, which is this way, is always negative. So the one thing that's missing in my equation here is in order for it to truly be accurate, I need to have a negative sign here. Because while theta is positive in this direction, alpha goes this way, right? Alpha's that way while theta's this way. So there's a negative sign relationship between the two of them that has to show up right here. In fact, in any type of restoring force, you're always going to have a negative sign, right? In the case of the spring force, it was negative k times x, right? Oh no, I'm frozen? Oh no, I'll wait. Looks like I'm back now. Well, let me just pause for a second because it says it's okay. It says it's running. Let me back up a second and say what I was saying. I don't know how long it was frozen. My God, my internet company is bad. It looks like it's good. I'll let people catch up because maybe people might have closed the stream and reopened it. So let me go back over what I was saying. What we're looking at here is why there's a negative sign here, okay? And the reason why is because the angle theta is defined as positive like this, and the angular speed alpha is opposite to that direction. So whatever one of them has to be negative. There's going to have to be a negative sign between the two of them. And the other thing I was trying to say is that this is always going to be the case with restoring forces. We'll see it show up again when we talk about physical pendulum. Because in the case of this box and spring, the restoring force here was equal to negative kx, right? And that's where it's always, x is positive in this direction, but the force is negative. So you have that automatic negative sign that shows up there, and you have to have that as part of this to get this to work out right. Okay. Now let's keep writing here. So now we're going to have negative mg times the sine of theta, and what we'll do is we're just going to replace. Well, I could have canceled the masses, right? We'll do that in the next line. We're going to replace alpha here with d2 theta dt2. Second derivative, right? And let's do some more. Let's do some other things. We'll have negative g over L times the sine of theta is equal to the second derivative with respect to theta. Once again, we find ourselves with a differential equation, just like we did last time. We have the goal of effectively solving for, although we're not really going to do it here, the value of what theta as a function of time is. That equation allows us to solve for that. But there's a problem. And the problem is that this equation, I don't think it has what we call a closed form solution. There's no simple function that will satisfy this relationship as far as I know. Okay. And I don't know how to best show that to you other than to say, can you think of any function, okay, that when you take the derivative twice, you get this stuff. Don't worry about that. The biggest thing is, can you think of any function that when you take the derivative twice, it gives you the sign of the function? You see what I'm saying? You have to get the sign of the same function back. So let me just give you some examples of things that will not work for this equation. At least not in the current form that it is. If we try, because we did this last time, we're going to do it again with this. If we try theta of t equal to like a and some amplitude, I don't know, multiplied by sine of, I don't know, omega t or something like that. When I take the first derivative. Can I use this just to save space? Theta dot means the first derivative with respect to time. I would get a omega times the cosine of omega t. And then I would do theta double dot, which is the second derivative with respect to time. I would get negative a omega squared sine omega t. And now the problem is, if I plug these back into my equation here, right? So now we plug them in over here. Let's use green. We're going to erase this. But I would get negative g over L sine of theta. Well, what's theta? Theta is actually this whole thing here, right? A sine omega t. And then this would be equal to this piece right here. Negative a omega squared sine omega t. Okay, and can you see the problem? It's almost right if we allow to say somehow that, like, the omega squared is equal to this thing, right? So that part's fine. They're just constants. We can work that out. But do you see the problem? It's the sine of this, and then it's the function. Can you guys see how this is just, that's not equals? Even if you make the assumption that omega squared is equal to g over L, you can't cancel out the a's, right? And so say, okay, well, what if we just get rid of the a? What does it look like then? So let's get rid of the a's. That's easy enough to figure out what that's going to look like. Get rid of all the a's here. Because you're like, oh, maybe that's just the problem. Let's get rid of the a. It still doesn't work, right? This says not sine squared, but the sine of the sine. Whatever that is. That's just a kind of weird thing to do. You take the sine of the sine of an angle. It's kind of a really strange thing to do, right? Because when you take a sine, you're usually taking the sine of an angle. So this is the angle, omega t. But, yeah. I'm belaboring this probably way too long. You guys see that this does not work? Okay, cool. So this doesn't work. Doesn't work. So what do we do? This differential equation is too hard to solve. It's just too hard to solve, unfortunately. It just is. We could get a we can get a computer and we can solve it. We can get a numerical solution for this if we want to, and then we can evaluate what it's equal to. But it just won't work. So we need to use some kind of a shortcut here. All right? And this is the shortcut that we're going to use. Okay? None of this stuff works. Oh, it's actually going to kind of work here in a second, so maybe I shouldn't. So we're going to take a shortcut, okay? So we're going to use what's called the small angle approximation. This is done very, very commonly in physics. What? A? What's up? Do you have a question, Summer? Small angle, maybe you've heard of it before, I don't know. Okay, small angle approximation. What is that? What we're going to do is say that as long as theta is small enough, so, well, there's two caveats for this. First, if theta is measured in radians, not degrees, but radians, then we can say, I think it has to be in radians, we can say that if I take, we can try degrees too, I just can't remember off the top of my head, that if theta is measured in radians, that the sine of theta is approximately equal to theta if theta is small. Okay, and what's small? It's like basically theta less than about pi over 6, which is, you know, equal to 30 degrees. So as long as that angle is small, like less than 30 degrees or so, then this is going to be reasonably accurate, okay? And to prove to you that this is true, that you can replace sine of theta with theta in this equation here, we're just going to do some calculations real quick with the calculator. So we're basically going to look at the sine of 0.01. Clearly a very small number, right? And we're going to put this in radians, and we're going to see what it's equal to, okay? So let me pull up the calculator. You guys do it yourself if you want. Like, put that into your calculator. Put your calculator in radians, right? What's the name of this one? EE-Web calculator. So put your calculator in radians and do the sine of 0.001. Okay. This thing takes so long to load. I really should preload it. Okay. So we're gonna do radians, right? And let's back this up so I can show what we're doing. So we're doing the sine of 0.01, right? Okay, so if I take the sine of 0.01, I guess I have to close parentheses. This is what I get. 0.0099999. Basically, you get 0.01, right? I mean, you can, for all intents and purposes, you get something like, we'll write down, flipped upside down. This is equal to, what is it, 0.00999. You get the idea. It's 4 9s and then an 8. That's about as close to 0.01 as you can get, right? And if you were to take a little bit bigger angle, like let's say we took sine of 0.1, then you're still going to get, let's see, sine of 0.01. It's, no, we just did that one, sorry. Let's take one of those off. Again, it's 0.0998, right? So you see that it's actually really accurate. And let's see how far it is off for this angle then. So suppose we put in pi over 6. So first thing we need to do is to figure out what pi over 6 is actually equal to. So that's pi over 6, right? So now we do the sine of that number. And look how close it is. So if I do the sine of 0.523, 0.524, this is basically equal to 0.5. Because, of course, that's the sine of 30, right? So since pi over 6 is, you can see that this is starting to get to a point where these numbers don't look like they're exactly equal to each other, right? I think you guys would agree that 0.524 is significantly different than 0.5, okay? But as far as the science goes and what we want to get out of this is kind of good enough to say that as long as you only displace through a small angle, that's why it's a small angle approximation, you're going to generate the frequency that we're going to observe, okay? There you go. There's one other way that you can see this too. You can see it graphically as well. So if we go to Wolfram Alpha, and we plot x and sine x on the same graph, I think that's more than enough to do it. If you plot x and sine x on the same graph, look at, if you just look, I can't zoom in, but look at this region between 0 and 0.5. So this is 0.5 right here, right? That's the place where you can start to see that these two curves are diverging from each other. But between negative 0.5 and positive 0.5, these lines line up almost perfectly, right? Within that region, sine of x and x are basically the same function. And that's why we can get away with saying this. And of course, you can look at it numerically if you prefer to prove the exact same thing, that this is a pretty good approximation. It's approximation nonetheless. It's not the exact solution. But for small angles, it's good enough from a mathematical perspective. Okay, does that make sense? Why you can do this? Anyone have any questions? This bothered me so much the first time I saw it in a physics classroom. I thought, oh my god, like they're cheating. Like physics, like this is the thing we want to solve, right? So why are we doing this? But it turns out to give you really good results, and it's like something we do in physics very commonly is that we have a problem, and we use Newton's laws, right? And it gets us to a differential equation. That's ultimately what Newton's second law actually does. Is it produces a differential equation that relates position to acceleration. And then once we've done that, we basically use an approximation to simplify our solution to come up with a nice simple solution that we can use. We do this so much in physics, it would blow your mind. Like the farther you get into physics, like almost every chapter, the first thing they do is they solve some differential equation and they make an approximation and they go with it. Our theories of quantum mechanics work this way because they produce problems that are too hard to solve. And so we have to make some type of assumption. And that assumption is often referred to as perturbation theory. And it is at the core of everything we do in physics to describe things on a molecular level, on a particle level. And it's just the nature of the game that you've got to approximate. What was it again? What did I say? The word I used was perturbation theory. Perturbation theory. It's something that you'll learn about if you get to Physics 1D, which you all should. Physics 1D is awesome. Perturbation theory, you spelled it right, Summer, that's right. Physics is all about approximation. That's what I learned after years and years of studying this, is that it turns out that we're really we're trying to approximate things, right? We're not trying to come up with these exact solutions. All right, let's see where this goes now. So there's our function, right? So now what we're going to do is we're going to take this and we're basically going to replace sine of theta with theta. So now our function is going to become negative g over L. That's a q. Negative g over L times theta, and then this is equal to the second derivative of theta, right? And now we've reproduced an equation that is very similar to an equation that we had from last time. I'm just going to show you what that equation was. Last time, when we had the box on the spring, we had a function that looked like this. It was negative k over m multiplied by x, and then there was a d2x dt, right? This is what we did last time in class, is we solved that equation, right? And what we found was that the negative k over m became omega, right? Omega was equal to the square root of this thing right here, right? So what do? In this one we say, well, g over L must be the frequency, squared at least. So you say basically let omega squared be equal to g over L. And that means that omega then is equal to the square root of g over L. And then because the period is 2 pi over omega, the period ends up being, and this is what we're going to use to solve problems, 2 pi times the square root of L over g. And that's our answer. Omega, the frequency of the pendulum, is the square root of g over L, and the period of the pendulum is 2 pi square root L over g. So these are the, period of what we call we call this a simple pendulum. It's just a mass on a spring. So what does it depend on? That was the question to begin with, right? So it turns out that it does depend on length. It does depend on the force of gravity. It does not depend on the angle, insofar as you just make the angle small enough, and it definitely doesn't depend on mass. This was something that Galileo discovered. He discovered that the period of a simple pendulum depends only on how long it is, and really that's it. That's 1D as in dog, Nate, that I was talking about, that you learned about that. It's in quantum mechanics. That's how you solve the hydrogen atom. The hydrogen atom has a solution of, or has a relationship when you're trying to figure out like where the electrons are going to be inside of a hydrogen atom, and the solution is too hard to solve in closed form, and so you have to generate you got to use perturbation theory. Is it hydrogen or helium? No, it's helium. The helium atom, my bad. So when you're talking about the helium atom. So the simplest out of hydrogen, we have a simple solution. It's not simple. But beyond that, we have to use perturbation theory to talk about more complicated atoms. Okay, so Galileo figured this out, and I think this is something that's worth mentioning to you from a historical perspective. Supposedly, and I don't know if this is true or not, but supposedly Galileo figured this out as a kid when he was sitting in church, really bored, and he was like looking up at the ceiling, and he saw all these big like chandeliers that had candles on them at the time, right? And these things would basically swing back and forth very slowly through small angle approximation. He's looking at these chandeliers, these big things that have all these candles on them, and they're swinging back and forth, and he's like timing how long it takes for them to swing back and forth. And he used his pulse, supposedly, to do this, and he figured out that the mass didn't matter, that it was just the length that mattered. He didn't know that the acceleration due to gravity was a factor, but it didn't matter. The point was the acceleration due to gravity for all the things he was looking at was the same, right? They're all swinging on Earth. So for him, he just said it's just the length. That's all that seems to matter for the period of a pendulum. And that's a really powerful thing to know, because if you think about it, it's a direct connection between distance and time, right? How long gives you how long it takes, the length tells you how long it takes to swing back and forth. That's pretty powerful. That means you can make clocks, right? This is the idea behind how a grandfather clock works, is that if you make the length, okay, I can tell you really quickly right here. If you want a clock, okay, let's say, then if you make the length a little, like not exactly, but a little shorter than 25 centimeters, then you can calculate right here. We can do it really quickly right here. So suppose we make the length 25 centimeters, and we come to here, okay? So if we make the length 25 centimeters and we look at our equation, it tells us that we take 2 pi, you multiply by the square root, so we'll just put it in parentheses, of L over G. So L would be 0.25, G is 9.8. And then we raise this to the 0.5 power. Yeah, there's 0.5, we'll do like that. See, it's almost exactly 1 out to like 3 digits right here. This would be a clock that would be off by 3 milliseconds every second, though, so it wouldn't be a very good clock, but it would still be pretty good. And you can obviously figure out exactly what number you need to put in here, right, to get a second by reverse solving this and saying if I take 1 second and I square it, and then I divide by 2 pi, and then I multiply by g, I think that'll give me the exact length. Nope, I did something wrong. T squared. Oh, you gotta square this part too, so you gotta divide by 2 pi twice. There we go. There we go. That's the exact length. 0.2482. If you could make it have that length, the second, it would be very, very close to a second. Right? So if you take this, for example, and maybe even just like cut it off like right here, let's say. Let's say you take a length of this, and then we go back up to our equation and we plug in that. You can see that it's very close to being exactly a second per tick. It would be off by 1 second, what, like every 25 microseconds, I guess? Very accurate clock, right? That all make sense to you guys? We'll do a problem with this stuff, but that all makes sense? If you want to make a clock, if L equals to 25 centimeters, you get basically that the period of said clock is almost exactly 1 second. And this is how we make clocks. This is it. Every single type of clock that has ever been made works off of this principle. We look for some type of a natural frequency within nature, okay? And we count how many times the object swings through it, right? So in this case, the equilibrium position means, suppose that I've got a pendulum, right? And I pull it over to here, right? And I let it go. What it's going to do is it's going to swing to here. That's half of a cycle. And then it's going to swing back again until it gets to here. And basically, that takes 0.5 seconds this way, 0.5 seconds this way, and that's 1 full revolution, right? Half the period this way, half the period back that way. And that's, 1 second. 1 second per swing, if you count a swing as 1, 2. I'm not specifically talking about the cesium atom, but you're right that the cesium atom, when it's subjected to certain types of microwave radiation, will have a natural frequency that comes out of it. And the way that that works is that there is electrons, I believe, that will hop back and forth between quantum states. And I think it's with flipping spins, or it's with jumping between energy levels. I can't remember which one it is. But the point is that it's, again, the cesium atom is our most, our current best type of clock, I think, because it uses the natural oscillations of this radiation that happens with the cesium atom, and you can use it to get clocks that have accuracy up to 10 to the negative 10 seconds. I think you could even go higher. I think you get to femtoseconds, which is 10 to the negative 15. So you can see that this type of a clock, right, is only going to be so accurate. We saw that if you use 25 centimeters, you're going to be off by 3 milliseconds. It's going to be 1.003, so that's not really going to work. So if you want a clock that's accurate within microseconds, you just make this more accurate, right? Isn't that also how they wanted to find dark matter when that clock messes up? Yeah, you use really precise clocks and look at the variation in their time when the gravity of the dark matter starts to affect the passage of time. That's right. But I really want to emphasize to you guys how fundamentally important this is for you to understand about our understanding of what time is. Okay, think about what do we mean by time, right? What is time? It's one of the things we talk about a lot in physics, but we don't address the philosophical understanding of what time is very often. Time to us is merely counting things. You know what I mean? We find something that is periodic in nature and we count it. The simplest example of this is the sun. The sun goes around the earth every 24 hours, right? And we call that a day. That's a unit of time. That's a unit of time is a day, because we know that the sun takes 24 hours to go around the earth. That doesn't really happen. The earth revolves on its axis or whatever. Doesn't matter. That's not what we observe. We observe the sun goes around a circle around us, and it takes a day for it to go around and then come up again and then go around and come up again, right? We also make another one, which is that we notice that the sun itself goes through cycles. It rises in the north, and then it drifts to the south, and then it goes back to the north again. And once you've completed one full cycle of that, that's a year, right? And it turns out that takes approximately 365.25 days, right? 365 and a quarter days. That's another type of natural motion within nature that we've discovered, a repetitive notion in nature that even ancient civilizations discovered, which is that the sun can be used as a type of a clock. Now, it's not a very accurate clock because it can only really tell you days and years, but it's a start, right? Because then we start subdividing the day up into parts. We say, okay, well, a day is composed of 24 hours, and an hour is composed of 60 minutes, and then 60 minutes is composed of seconds, 60 seconds, right? And then we say, okay, well, if we want to get a really precise clock, we better be able to measure down to a second. But even nowadays, it turns out that even measuring down to just a second isn't enough, right? We want to go deeper. So we start to make clocks like clocks that you can go buy at a store. Let's give you an example. You guys ever seen those type of wristwatches that say quartz on them? You guys know what I'm talking about? It'll be like I don't know, people don't really use wristwatches these days, do they? Everyone's got phones. There's no point, right? If you have a watch, it's probably gonna be a smartwatch, whatever. But so like older type of clocks, you can find these if you go to like a pawn shop or you go to a jewelry store or something like that. You might see some ornamental watches, and somewhere in the watch itself, it'll usually have the word quartz in it. If you haven't seen it before, I guess I could pull up a picture or something. But it's basically the way that type of a watch works is there's a crystal, okay, and you feed electricity into the crystal, and it causes the crystal to ring and vibrate at a certain frequency. And because the frequency is natural and because it's repetitive, you can use it to make a little tiny watch that operates off of a battery plus a crystal. That when you combine the battery and the crystal together, you get repetitive motion, right? I think that's pretty cool. But the point I'm trying to drive home to you guys here is that what we think of as time, right, is purely counting periodic vibrations in nature. It comes entirely from this. Our understanding of what time is quite simply counting the passage of repetitive motion. And that's all that it is. It's nothing more extreme than that. It's quite simply, we find things that we can use that are repetitive and we count them. So that's all we know about time. It is one of the most complicated things, I think, to understand. But in reality, when we measure time, that's how we're measuring it. Right? And time's really fascinating because as you will learn as you go through your studies, especially when you get to 1D, there are ways to alter the perception of time. And remarkably, all clocks that we use to measure time are altered in exactly the same way. So, I'll leave you to find out about that in 1D, but it's really interesting. There's all kinds of other things we can say about time. You know, you can say things like, sometimes it seems like time is traveling more quickly, like if you're at a party or watching a movie you like or something. Sometimes time travels more slowly when you're like sitting in a lecture and you're like hoping it'll end, or when, I don't know, you're on the bus and you're waiting to get to your next stop, or when you're just sitting waiting to get picked up or something like that, right? Psychological? Yeah, it is psychological. That's what I'm saying. I told you everything you need to know about time before I started to take these other things, and I'm saying these are some other things that we can say about time, but they're not directly related to what I'm talking about, is what I'm trying to say. Like, any one of these type of clocks, right, would... Any one of these type of clocks that we talk about right here would tell you that time always travels at the same rate, right? Time is a concept of human perception. It is. And time is like a man-made construct. Yes, it is. It is something that we've placed on the universe, that we've used to understand the universe. And it's been very successful, right? Our understanding of how we can count time and how to count it very accurately has allowed us to uncover secrets of the universe, right? That's a very bold thing to say, but I mean, it has, in a way. We've developed precise measurements of time. We've used those to just get better and better at things, right? I mean, what's a really simple example? I mean, if it wasn't for really precise time, we wouldn't be able to have competitions like, the 100-meter dash or something like that, right? Where to judge between one Olympic to the next Olympics, or from one, contest to the next, who the best short distance runner in the world is, we just accurately measure the time that it takes for that person from the start to the finish, right? And to get better and better at that sport, you need to be able to time yourself, right? You need to be able to time yourself accurately. And that's allowed us to kind of grow and expand ourselves as human beings from an athletic perspective, right? But we've also obviously used time to measure things like related to atoms, to understand about how they behave and how they work. And then understanding of time is directly related to being able to measure velocities. And so we've been able to use our understanding of time to basically predict and understand what things are made of, right? Understanding how quickly things move is one of the best ways we could determine things like what their charges are and what their mass is and stuff like that when they're super small and we have no way to actually measure them, right? So our understanding of time has been very successful, but it is nonetheless, as you guys say, a human construct. And it's definitely a concept of human perception. It's possible that there are other types of vantage points at which you can look at the universe, wherein time is simply a fourth dimension, and that we actually are living in some type of five-dimensional space or something like that, and that maybe there are civilizations and types of aliens that can observe and understand the universe, where time to them is just another axis, right? Another perpendicular to the XYZ that we think of, right? But for us, it's required, because we perceive this always. We always perceive the passage of time, except maybe when we're sleeping. Anyway, time is about counting. Time is about counting. Counting repetitive motion. And I think it's really important that you guys understand that, because I think that, well, I'm just going to leave it at that. Don't think it's anything else. It's the that's all it is. It's just counting repetitive motions in nature. Do you guys have any comments, or you want to talk more about that at all before we do a problem? So this is a neat problem about time. So given a simple pendulum with a period of 1 second at sea level, when taken up to a mountain top where g is reduced by exactly 0.1%, find the change in the period. How many seconds would a clock using the pendulum gain or lose in one day? Okay, so given a simple pendulum with a period of 1.00000 seconds, so really accurate, right? Seconds at sea level. When taken up to a mountaintop where g is reduced by 0.1%, find the change in period. Okay, so we've got our pendulum, and like let's say this is the ground, okay, and it's oscillating back and forth. Okay, and we say that the period, we'll call it t1, is equal to 1.00000 seconds. Okay, and then we take the same pendulum up to the top of a mountain. Right, so we put the pendulum up here on the mountain, fastened to something that's above the mountain. Maybe a stand of some sort that we put it on. And we say the period here, we don't know what it is, but we want to figure out what it is. What we know is that if we call the acceleration due to gravity down here just equal to g, our normal g, that's, the 9.8 meters per second squared, that when we come up to here, g2, the period on top of the mountain, you guys know that the farther away you get from the center of the Earth, gravity goes down, right? So up here we're going to say that it's reduced by 0.1%, and 0.1%, right, just to be clear about this, is basically equal to 0.001. So g on the mountaintop is going to be, I would say, 0.999 of g on the ground. Right, is that clear? Because it would be reduced by that, right? So you have to take 1 minus. And that's how you get that. So our equation that we're going to use is this one here. Period is equal to 2 pi times square root L over G. So we know that T1 is equal to 2 pi square root. Now the length is fixed here, by the way. Okay, it's fixed to some value. The length is not going to change. It's the same pendulum. Okay, so it's 2 pi square root of, is it L over G? Yep. Length divided by, the longer it is, the bigger the period's going to be. Right. And then we know T2, we'll write it right here, is going to be equal to the same 2 pi times the square root of L. But now we're going to divide by this guy. Okay. Our goal is to find what this is equal to. So in order to simplify that, what we're going to do is we're going to divide these two equations. This one over this one. And we'll see that a lot of things cancel. We'll end up getting T1 divided by T2 is equal to, the 2 pi's cancel, the L's cancel, and what we're left with is this. Which really means that T2, see if I get this right, T2, we're going to have to solve for that. So I think what we're going to get is that T2 is going to be equal to T1 divided by, you see the G's cancel here and here, the square root of 0.9999 said that T1 was 1 second, right? So then we just put in, I'll leave it like this, but then we just plug in 1 second. You guys have any questions? So that's the, we can find the change in period too if we want, but this is the value of the period. Obviously the change is like this number right here. And if we did T2 minus T1, we would get 0.0005 seconds. That's the change. Does that make sense? Hope I didn't go through that too fast. You could solve this other ways too. You could solve for what the length is. The length is like 0.2486 something. And then you could use that to plug into this equation and then just directly solve for T2. You get the same answer, but by doing this ratio method, you prevent yourself from losing digits due to rounding and stuff like that. So I prefer this method. I always like using ratios if I can. They're always more accurate because they eliminate constants that we have to otherwise approximate with our calculators. Right, because pi is... What we plug in for pi is always going to be an approximation, right? Guaranteed. You have to stop... You only put so many digits of pi into an equation. So there's going to be natural rounding errors if you don't do this and cancel out the pi's and the g's and stuff. Because the g's also have errors on them too. Right? Anyone have any questions? Do you know something about this, by the way, in terms of the power of what this says? If I know that T1 is 1 second here, and is G irrational? I mean, no. Well, I mean, this is what it's equal to. You take the mass of the Earth and you divide by the radius of the Earth squared, right? And then you multiply by big G. So no, that's not an interruption. It's a really good question. This is only known to so many digits. This is only known to so many digits, and this is only known to so many digits as well, right? So every one of these numbers is, you have to stop the, like, I mean, you've done this in the one lab we did, right? There's going to be error on this number, right? Because there's error on G, there's error on the mass of the Earth, and there's error on the radius of the Earth. And all of those errors combine together to give you a value for G. You know, we usually say that G is equal to something like 9.81 meters per second. But there's a plus or minus here too, right? It's plus or minus something. I don't know what it is. We could go look it up on the internet if we want to, right? So I wouldn't say that G is irrational. I would just say that there's a point beyond which we don't know what the next few numbers are. Does that make sense? There's a point beyond which we don't know what the next numbers are because we only know each of these other four numbers to so much accuracy, right? And that limits the number of digits we can write for G. So it's not exactly irrational so much as it has a fixed limit because it's a scientific measurement. And like all scientific measurements, like, there's always a point you have to stop what you're doing, right? There's only so much information you have, and beyond that, you're just looking at errors from a calculator or something. All right. So, any other questions about this? So this is what I want you guys to think about. Suppose that we didn't know this, right? And we took a pendulum from one location and we pulled up to another location here, right? And then let's say that our pendulum was really accurate, and that we could test, we could test moving from here to here what the change was, right? I mean, this is a really easy experiment to do, right? You could do it here in California. You go buy yourself a stand of some sort or whatever. You take a string, you attach to the string a ball, right? And then you get some kind of like support. Tie it to the ceiling or something, I don't know. Tie it to the top of your car or something like that inside, right? You displace the pendulum by some amount. You let it swing back and forth and back and forth and back and forth like 20 or 30 times. You time how long that takes. You divide by the number of oscillations, you get the period, right? You perform that experiment, let's say 20 times, right? You let it swing back and forth 30 times. You calculate the period. You get a really good idea of what the period of the pendulum is, right? Then you take that exact same pendulum, you drive up to the mountains, right? You drive up to the mountains, right? And you hang it from the ceiling of your car, and now you do the same experiment again. You let it swing back and forth 30 times, right? You count how long it takes, divide by 30, that gives you the period, right? You're going to get different answers, right? You're going to get one answer for the ground, maybe it's 1 second. You're going to get one answer for up here, maybe it's 1.003 seconds, I don't know. And they're going to be off by a little bit, right? You could literally use that to figure out exactly how much G is different from one location to the other, right? You could quite literally figure out the variation in the gravitational field of Earth based on height, right? Then you could also use it, if you wanted to solve for the height of the mountain. Does that make sense? You could literally use it to solve for this height right here. You could use a pendulum, which measures time, to tell you the height of the mountain to some degree of accuracy. I think that's really powerful, right? But there's something else you can do that I haven't really told you about the way gravity works. So if you think about the Earth, right? You know the Earth has some kind of a core that's solid of iron right here that's very dense, right? And you've got the mantle and you've got the crust, right? That's our kind of simple version of this understanding of what the Earth is. But within the crust and within the mantle, possibly, there's often big pockets of things, right? There's underneath the surface of the Earth, I don't know if you guys know this, there's big reservoirs that are filled with something that's reasonably valuable, which is natural gas. Yeah, natural gas is an actual gas, but there's like these pockets of this gas, right? Now, when you're calculating gravity, okay, you know, we know gravity is acceleration that goes this way, right? It actually depends directly upon all of the matter that's contained directly beneath this object, right? And so if you imagine that at a different location, maybe there's no gas, and it's just much denser right here, right? So if this is dense, and then due to the fact that there's some gas right here, it's less dense within that region that I'm, right? Then in a pendulum that was designed, well, let me back up a step. If this is less dense, then G is going to be greater right here. Maybe G right here is like 1.01 G or something. Because of the density of the material beneath your feet, and because gravity is a function of mass, if there's more mass right here than there is in this region over here, then gravity is going to be higher here, right? So this is going to be bigger G by a tiny, tiny amount, maybe like the 1/10% or something like that, like kind of what we're talking about here. So this would be a bigger G, and then this would be a smaller G, right? So what could you use this to do? You could literally have a pendulum that's designed to tell you if there's a huge pocket of gas directly underneath your feet, right? And then you could use that as a reason to go start up a mining operation and go extract that gas and then process it and sell it. Does that make sense? You can literally see what's underneath the Earth with something as simple as this. You can use this as a way to measure gravity. Because if the length is fixed, then the only thing you have is G. And the period is something you can observe, right? You can observe the period by letting it swing back and forth, and you can use it to measure the gravity there. And if you can measure the gravity, you can use it to find gas. So you can quite literally use it to make money. And geologists actually do this. They actually use devices like this to figure out where there are pockets of less dense material, which almost certainly is like either a gas or possibly a liquid, some type of reservoir of, oil or natural gas. Does that make sense to you guys? Is that interesting at all? I find it fascinating. But, yeah, I don't know. So, there you go. You guys have any questions? All right. So, I was going to talk about a physical pendulum, but it just isn't that interesting, and I really would much rather talk to you guys about resonance. So let's talk about that, and that will be the last topic, which is a very appropriate last topic for physics. Before we move on, do you guys have any more questions about pendulums? You're going to have a few problems in your homework. Just understand the period this is all you need to know about pendulums right here. That's it. All you need to know. Oh, we didn't solve the second part. Sorry. How many seconds would a clock using this pendulum gain or lose in one day? A clock using this pendulum, how many seconds would it gain or lose? Is it going to gain seconds, or is it going to lose seconds? Think about that. Will it gain seconds, or will it lose seconds? What do you guys think? You can answer in the chat. Gain? Lose? Gain? Okay. It's good to see that there's some some dispute. It's not obvious. I don't think it's obvious. Will a longer period lead to a clock that's behind or ahead? Let's see. So, for the clock on the mountain, right? For the clock on the mountain, this becomes the new second, right? This becomes the new second. It literally takes a little bit longer to tick a second by this much every single day. It takes that much longer every second, right? Every second, it takes that much longer to actually tick on the clock, yeah? To tick on the clock. So it basically is going to have a change in time up here that's going to be that every second it loses 0.0005. So you lose. I gotta erase that, just looks really bad. Sorry. 0.005 seconds every second. So to figure out how much it loses every day, you need to multiply by the number of seconds in a day, which I think is 86,400, but we won't write it like that. So we have to basically say it's every second it loses that. So you need to multiply by 60 seconds per minute. Oh, whoops. 60 seconds per minute multiplied by 1 minute. Oh, okay, whatever. I'm just going to write it this way. If you take 3,600 and you multiply by 24, what you get is 86,400. That's the number of seconds in a day. That's what I want to write. I don't know how I was supposed to get there, but this works, right? 3,600 times 24, you're going to get this. Check that for me if you guys want to. So it loses that many, it loses 0.0005 seconds every second. So if you multiply by the number of seconds in a day, you get the amount of time that it loses per day. It's right, thank you very much. And then, yeah, because I could have put 84.6. I mix that up sometimes. So if we take 86400 and we multiply by 0.0005, you get 43.2 seconds. So this clock would be off by 43.2 seconds, which I think you guys would agree is a lot. If you have a clock that's off by that many seconds per day, it only takes like, I don't know, 60 days, and it's off by 45 minutes or something like that, right? Something like that. Doesn't take much. It's off by about almost a minute a day, you could say. So after a month, it'd be off by like 30 minutes. So now it's going to say that it's midnight, but it's actually 11:30. And if you let it run for a year, it's going to be off by what, like, if it's 30 minutes a month, it's going to be something like 6 hours. So by the end of the year, it's going to say midnight, but it's actually 6 p.m. and it's going to be bright outside, right? So at this rate, the clock would be way off very quickly, right? It would not be a very accurate measurement of time. I think that's interesting to understand that. But this is only clocks that are based on gravity, and not all clocks are based on gravity, right? Like, the clock on your phone is not based on gravity, for example. All right, so yeah, let's talk about resonance now. This is going to be a very brief discussion, but it's something that's really, really important. Okay. So I want you guys to consider, I feel like I've used this analogy in this class before, but I don't know. Let's consider a system that is very similar to a pendulum, okay? Let's consider a child that's on a swing. So we've got a swing, so it's fixed from here up somewhere, and we have a child that's sitting on the swing, that's swinging back and forth. I guess they would be kind of sitting and holding, I don't know how to draw this, this is stupid. Like this, like this. So they've got their legs on the swing, and then they've got their arms holding right here, right? And they're swinging back and forth. Now, resonant frequency, okay, means the frequency at which the system naturally wants to oscillate, okay? So if this is an object that has a length L and it's subject to the Earth's gravitational field, then if this person is swinging back and forth, they're going to swing back this way, they're going to swing this way. And the so-called resonant frequency of this system is just what we calculated a second ago. it's going to be equal to what we call the square root of L over G. Sorry, G over L. Right, that's that right there. Okay, that's what we call the resonant frequency. This is basically the frequency that it naturally wants to oscillate at. It's independent of the arc of the swing. The person's basically going to oscillate back and forth at this frequency, even as over time, if the person's not putting any energy into the system, even if the person just lets themselves swing, even as the arcs get smaller and smaller, the frequency doesn't change, as it turns out, because it's independent of the amplitude. It's constant frequency, right? Okay. And of course, this also corresponds to a period that's equal to 2 pi times the square root of L over G. Now I'm going to use this as an example of how we can talk about driven oscillation. Let's say that our person is swinging back and forth at a period of 2 seconds, okay? So they go up and then back to here again, and it takes 2 seconds for that entire process. Does that make sense? So let's suppose that while this is happening, as is frequently the case if you go to a park with your young relatives or whatever, or your siblings, let's suppose there's a person that's pushing. Okay, so this person is pushing this child on the swing. Now, if you want to make the child go higher and higher, how frequently should you push them? Okay, so if the goal is to make the child go higher and higher, to increase the amplitude of the swing, you might say, the question would be but how frequently do you push? Do you do it every half second? Do you do it every 1 second? Do you do it every 2 seconds? How frequently should you push this person if they're swinging back and forth to guarantee that the person goes higher and higher? Every 2 seconds. That's exactly right. Because if you do it any more frequently than that, you're actually going to do the opposite of what you want, right? Let's say you push every 1 second, okay? What's going to happen? The person swings up, and then they get back to here, but they're going in this direction, and you're pushing them to the left. That doesn't work, right? That's actually going to make them stop, right? And then they swing back this way after you push. They swing back to here again, and now you push while they're going this way. Well, that's actually going to help. So then you realize, oh, I don't want to push them every second. I need to wait for them to... I push them when they're here, right? To give them to get going. They swing this way, and then they swing back to here, and then they swing back to here again, and at this point, you push them again. And that whole time takes 2 seconds, right? It goes this way, that... So you start from here, you give them a push, they swing this way, and they swing back this way, and they swing back to here, and at that moment, you're going to give them a force again. Right? Every 2 seconds. The answer is every 2 seconds, you need to push them, basically. And that will guarantee that the person continues to go higher and higher and higher, okay? We call this phenomenon driven oscillation, where you have an external force that's forcing the system to oscillate, and when you drive the person with a force that is the same as the resonant frequency of the system, or the natural frequency, then you guarantee that you're going to have bigger and bigger amplitudes with every single swing. You're constantly going to be inputting energy into the system at just the proper rate, so that the person gains amplitude. And this is easy to do, right? Certainly this is something you guys have all done, either as kids or you've done it as adults. You go to a park and you want to, get your niece and nephew to go as high as possible, and so you push them and you push them, and you make sure every single time that you push them that it's when they're swinging up every time. And if you do that, they'll go higher and higher and higher until they get scared or something and you have to slow down. But yeah, does this all make sense to you guys? This is a phenomenon that occurs all over the place in nature. It's one of the main ways in which we probe physical systems. The force needed to increase height is equal to the... It's not that the force is equal. You can use any kind of force you want. It's the rate at which you use the force, Ariana. It's the rate at which you use the force, right? So I'm going to type out what I just said in words, because it's going to be kind of a long sentence. Like, right? So if... call this effect resonance. This is the assumption of the force. It doesn't actually have to be the same every time, as it turns out. It doesn't even matter. It doesn't matter if the force is small or big. Eventually, this person will go higher and higher and higher. Guaranteed. It doesn't matter. I mean, I guess if the force was less than the amount of kind of force that the person would need, I don't know. But basically, it's not necessarily the force doesn't have to be the same. In fact, what we're going to talk about next is suppose that you could apply a force at every point that was parallel to the velocity, right? Suppose you applied with a force that went this way, and then that way, and then this way, and then that way. That would make them go even higher, right? So if I change one caveat, which is to say we put two people here, we put one person here, and we put one person here. If this person pushes every 2 seconds on the upswing, the person on the left pushes every 2 seconds on the backswing, the kid would go even higher, right? As long as the force is parallel to the velocity at every moment, then the force is going to increase the velocity, right? You'll have positive acceleration in every situation. All right, child on a swing is the simplest example I can give of this, okay? You can experience this effect if you want to with just a pendulum. You take anything that's got a cord and you hang it and you just swing it, and every time it swings, you push it, right? This phenomenon occurs a lot in nature, that you can discover things about a system by figuring out what the resonant frequency is. And to find out what the resonant frequency is, you just need to figure out how often you need to apply the force to actually make it keep increasing inside. And let me give you, I've got a video for this one that's pretty good. We don't have anything like this at our, we have something kind of like this. There are types of demos that I can show you that are like this, but this one happens to be really good. So what we have here is, there's a mass that's connected to springs on the top and bottom, okay? And because there's a spring on both sides, this mass, if it's given a small displacement, will undergo simple harmonic motion of the type we discussed last time. There we go. Because it's a mass and a spring, right? So it's going to oscillate up and down, right? But what we have down here is a frequency generator. What's a frequency generator? A frequency generator is basically going to cause this little thing at the bottom right here to oscillate up and down. See this little piece right here? And I'll let the person take it from there. I remember, if I put captions on? Annotations. It should, that does it, right? That makes it have captions? Because I know you guys can't hear the sound. So I'm just going to kind of turn off the sound on my side and just kind of, he's going to explain a lot of the stuff that I just did. But watch this. This is really powerful in my opinion. This is one of the biggest like kind of tricks by which we understand science, by which we find things, you might say. Is he gonna say? I'm gonna leave the video on for a second. I don't know. Why isn't it doing annotations? So this is the rate at which this is. He's changing the frequency with which this thing is going up, down, up, down. This is in hertz, so it's 1 time per second. He's increasing the frequency. He's going faster. The scale's in centimeters is what he's saying. It's like 2 centimeters, 4 centimeters, 6. Notice how little is doing. He's at 2 hertz. He's going to raise it higher. He's basically looking for the resonant frequency. Does that make sense? He's trying to see a place where this thing starts to go crazy. So 2.5 is not working. Okay, now he's at 3. It's starting to oscillate a lot more, right? And then all of a sudden, look how much it's oscillating. The amplitude went from being like a centimeter to now it's up to like 14. He's trying to match the correct frequency. Now watch what happens. He's going up, right? And then it dies off. Do you see that? So like this is the most important effect. Like, so we go back to where it was like 3.3, right? Look how big the amplitude is, right? You might think, okay, well, what if I just go faster? There's the natural, yes, it's the natural oscillation. So as he goes up higher, though, you lose the effect. It's like a sweet spot. It's like a sweet spot with which you got to push it every time it's coming back at you. You need to push it. But notice that, can you see? Like if you look at when this goes up, it's coming towards it, right? See, it goes up and it's going down. So if he goes back to 3, it's not about speed, right? It's about the right. It's like about the sweet spot, finding the sweet spot. And you notice right when he gets to this, it gets crazy. It just goes, and it's just oscillating like crazy. And at this point, the only thing limiting how fast it could oscillate up and down and the amplitude of the swing is quite literally the size of his system. If he made it taller, it would see, it's hitting the bottom, right? It's dampening out some of its energy. So, and what he's saying is what I just said to you guys now is when the force applied here is at the same frequency as the resonant frequency, then you get this effect, right? It's just like the child in the swing, right? Except that it's a mass on a spring. And just imagine that there are tons of phenomena in nature that look just like this. Just like this. And we use it to solve and understand things. It's one of the main ways in which we probe our universe, is by looking at this idea called resonance. And I'm going to point some things out to you that you probably heard of before that you didn't even realize exhibit this phenomenon. You guys have heard of an MRI, right? An MRI is something that we use to get a vision inside of our body of like cells, right? Of tumors and stuff like that, right? It stands for magnetic resonant imaging. It uses resonant phenomena like this. In the case of the MRI machine, it's the resonant flipping of spins for certain nuclei. And it uses those to probe and see where things are. It's a resonant process. You literally look and probe by scanning over frequencies. If you guys are taking chemistry, you look at what's called an NMR, which is a nuclear magnetic resonance device. Have you guys looked at NMR images in your chemistry classes? Maybe not yet. You will. If at some point in chemistry you're looking at an NMR, that R stands for resonance. Okay, you're driving the system right at the frequency that it really wants. This is one of the primary ways in which we observe and understand the most fundamentally small things in nature. And it just comes up all over the place in physics. All over the place in physics. One of the ways that we search for elementary particles, what I did in my field, was by probing the energy at which you get a spike in production of particles and stuff like that. And it's also a resonant phenomenon, as it turns out, that you get the biggest amplitude when you're right at the proper frequency. That's resonance. It's a nice thing to finish up 1A on. Do you guys have any questions? All right, I'm going to stop the stream now, and I will stick around, of course, if you guys do have questions.